what about the work done by this dissipative internal force of friction? Well, it is the integral of the friction force dotted with displacements along the total displacement. So this is the friction force, this is a vector dot product, and I'm going to go, right, because I'm studying the case of going from 0 to S. I'm going to study how much work was done by this dissipative friction force from 0 to S, like this. And so if you think about it, right, as this, so Fk is up the plane because friction is backwards to the motion is down the plane, so friction is trying to restrict that motion. So this is the direction of the friction force, it's up the plane. But the dS's, the displacements while you go down the plane, are in the opposite direction. So when you do this dot product of anti-parallel vectors, anti-parallel vectors, the dot product gives a minus sign. So this is going to be minus the magnitude of F sub k times the displacement S, where S is a positive number. So the minus sign comes from the dot product of the anti-parallel vectors. F sub k is constant, that's why I could pull it out of the integral and do the integral from 0 to S of ds, like this. And F sub k is just mu sub k times the normal force. So I have to figure out what is the normal force. I'm going to treat mu sub k as a given. So it turns out, and the reasoning comes from Newton's second law. So in Newton's second law, what we know is as the block goes down the plane, here's the block can only have an acceleration either down the plane or up the plane. If it's down the plane, it's speeding up. If it's up the plane, it's slowing down. So what this really means is that the gravity force is, so this is mg, this is the weight force. We should consider it in two different directions, a direction perpendicular to the plane and a direction parallel to the plane. Can you see this dotted line is meant to be parallel to the plane? And this right here, this angle theta between perpendicular and the weight force, this angle theta actually matches this angle theta. So the angle of inclination of the plane is the angle difference between perpendicular and vertical. So this side right here, the perpendicular side, is mg cosine theta. And this is what must balance with the normal force. This right here is the condition that F net in the perpendicular to the plane direction is 0. I know that there is no acceleration perpendicular to the plane. No acceleration perpendicular to the plane means that the forces that are perpendicular to the plane must add to 0. So this is the condition that a normal force plus mg cosine theta in the opposite direction, those two arrows, they add to 0. So back over here, we can say that the kinetic friction force then is mu sub k times mg cosine theta, like this. So that means that the work done by the dissipative internal force from 0 over to S is simply equal to, so there's that minus sign, there's Fk, and then another S right there. So it goes minus S mu k mg cosine theta. So right now I've got a function that describes to me the potential energy of the block as a function of distance down the plane, and I have the work dissipated as a function of distance down the plane. So there's that S right there. So it goes from 0 to S, right? So I can go and fill in this conservation of energy statement. So instead of S1 to S2, I'm going from 0 to S. So I'll say that the mechanical energy at S minus the mechanical energy initial at 0 is equal to this dissipative force from 0 to S, the dissipative energy, and it is value minus S times mu k mg cosine theta. So what does this give us? Well, what it gives us is really apparent if we write down the next thing. We write down what is the mechanical energy as a function of S. Well, it's the kinetic energy as a function of S plus the gravitational potential energy as a function of S. So we've already done that. And the kinetic energy as a function of S is actually 1/2 m the velocity as a function of S squared. So this kinetic energy is a function of S, so m doesn't vary with position down the plane. M is it's a fixed value, but the velocity does change, and the kinetic energy depends on that velocity squared, so it just goes like that. So then I can put this, though, is, so u sub g, I have this minus sign, so let me scrub that out. So minus S times mg times the sine of theta. All I did was move the S to the other side, so there's the minus sign. So this is the mechanical energy at position S. And it's interesting to write down what is the mechanical energy at position 0. It's the kinetic energy at position 0 plus the gravitational potential energy at position 0. But the gravitational potential energy, we chose it to be 0 at position 0. So this is 0, but this is not 0. This is 1/2 m v initial squared, where v initial is, as described in the problem, is just the initial sliding speed when you cross the position s equals to 0. So now we have, all of a sudden, because of this statement here, we can write that 1/2 m v of s squared minus s mg sine theta. So that is the mechanical energy at position S. That's what goes in first. Then you put a minus sign. So there's a minus sign on the quantity of 1/2 m v initial squared, like this, is equal to, so by the conservation of energy, we say that the mechanical energy changes because of this dissipation work. So here's the dissipation work here. So minus S mu sub k mg cosine theta. And this right here, imagine if you were given the mass of the block, the initial speed of the block, and the coefficient for kinetic friction, as well as the angle theta. You already know the value g. So g goes here, m mu sub k. Cosine of theta, it's one of the givens. It's sort of part of the geometry of the problem. But the point is you can see that what we have here is a way to solve for, this is the only place that v of s is. So you could move these two terms to that right-hand side of the equal sign, multiply both sides by 2, divide by m, take the square root, and you can get a function v of s. So this right here is interesting kind of knowledge. So some things you might expect. So v of s, interestingly, what about this? So v of s as a function of s, so here is the independent variable, here's the dependent variable. We know it starts at v naught, and there's a situation where it does not change. that is, the speed is constant as a function of s, this would be the situation of being at that critical angle. But we could have a situation where the velocity as a function of s increases. I'm not sure how it increases, but it's going to increase. I don't believe that it's linear as a function of s. Although, interesting question, like what kind of function of s is this? This would be the situation where we were steeper than the critical angle, right? That's the steeper. And then there's the situation where angle theta is smaller than the critical angle, and we expect the velocity to shrink off to 0. So maybe, probably, actually I don't know, like it could follow a curve like this, or it could be like that, or something like that. But anyways, where the velocity crosses the s-axis, this, whoops, is the max s, right? The max s is the thing I was alluding to here, right? There is a max, so that's where the velocity ends up at 0. That's where the block stops because we have too shallow an angle. So it's interesting to study these v of s's. It's interesting, if you go and you ask down here, what if I look at a position that is bigger than s max? It might be that this could evaluate to be negative, which makes no sense. But I wonder if the velocity could, for s values that are bigger than s max, right? These are impossible values for s for this problem. It could be that this kind of velocity is a complex number, which also makes no sense. These could be outcomes of this kind of work. It turns out that theta star is actually equal to the inverse tangent of mu sub k. And this is regardless of m or g. So that special critical angle, such that the velocity doesn't change, is actually, dependent on the coefficient of friction, but independent of how strong gravity is, or how much material is involved, or how much inertia.